My plan for today is to do the same thing I did last time, which was split the lecture into two parts. I want to cover a part where is applied material, which is the stuff you need to do the labs, and the other part is the conceptual material that is what the exams will focus on. Last time, though, I covered the conceptual stuff first, and then I ran out of time before I got through the applied stuff. So we had to make up that lecture in lab, and it took away from your lab time. So this time I'm going to cover the applied material first. I'm going to begin with talking about the MIPS ALU, and then we'll talk about test benches and simulation. And then if I get done with that, then I'm going to switch to the conceptual stuff and talk about timing and timing of logic circuits. So the first component we're going to build for our CPU is the ALU. And in fact, I'm going to give you the code for the ALU. And your job for Lab 2 is going to be to write a test bench to test it. So you can get some practice on how test benches are made. The ALU is a 32-bit ALU. It'll implement 13 operations: add, subtract, multiply, multiply unsigned, bitwise operations, and, or, nor, and XOR, two comparison operations, which is set less than and set less than unsigned, and then there's three types of shifting operations: shift left logical, shift right logical, and shift right arithmetic. In the MIPS, RISC-V, and ARM instruction sets, there are instructions that there's multiple instructions that essentially just do one of these operations. Like, so, I'm sure you remember from 212, there's an add instruction that adds two registers and puts the result back into a destination register. And obviously, this ALU will do that, except right now we're just designing the ALU and not the surrounding logic that will decode the instruction and handle the registers. Does that make sense? You guys with me? Yes?
Why not division operation?
I tried division. I used the Verilog division operator in the ALU, and when you have it do that and you design it to be combinational logic, in other words, you want it to do the whole divide within one cycle.
Okay.
It took up like the divide logic took up almost all of the FPGA. So it was really expensive. Now I think we could fix that by creating like a multi-cycle divide, which will allow it to perform the divide over multiple cycles, and that way it gets to reuse hardware for different steps of the divide operation. But if you try to do it combinationally, it eats up the whole FPGA. So that's the reason why. And to do a multi-cycle divide, you would have to have extra logic in your CPU for handling stalls. Like when the divide is fetched, you'd have to stall everything behind it while you perform the divide.
In addition to like pipeline logic.
Right. Yeah. So it would be a little bit more complex. It's possible. I've thought about adding that to the class, but we just don't have enough time to get to it.
Okay.
Okay, so the interface for the ALU is two 32-bit inputs, A and B. There's a 4-bit op operation code, whatever you want to call it, that tells it what to do. There's a 5-bit shift amount, which is treated as a don't care if you're not doing a shift operation. And then there are two outputs. This is the part that is always confusing. Most operations will only use the low output. The only exception to that is the multiply and multiply unsigned, which use both the high and low, because when you multiply two 32-bit numbers, you want to be able to have a 64-bit result. So what that means is that the high is a don't care for every operation except the multiply. You just ignore it unless you're doing a multiply. So for most practical purposes, low is the output. It's a 32-bit low is the output, except for multiply when it's the concatenation of high and low together, both of which are 32 bits. And then there's a single bit output called 0 that is a flag that indicates whether the result of the operation you performed on low is 0, and it's a flag, so it's a 1-bit signal. It's either yes or no, true or false. Make sense? So that signal is going to be used when we're implementing branch instructions, and that will be our branch resolution signal. So we're going to implement a branch of equal to BEQ, and so when you do that, the CPU will subtract A and B, and if the result of the subtract is 0, it means A and B are equal, and that flag will go high, that 0 flag will go high, and that'll indicate to the control unit that the branch should be taken. Now, the only thing we have to worry about is setting that to 1 whenever the low is 0. You guys with me? Okay. So this is a symbol view of the ALU. I think I got this from the book. I don't know why they have it oriented sort of top to bottom, where the inputs are on the top, outputs are on the bottom, and then there's the 2 control inputs are on the side. I don't know why they drew it that way. Normally it's, the data flows from left to right. But that's like a symbol of the ALU. And then this table shows how each of the ops translate into functions. So if the op is 0, 0, 0, that means that the ALU should be doing a bitwise AND. You guys with me? So this slide is something that you're probably going to refer to as you build your CPU. This is a nice reference slide because this has all the ALU opcodes and what they mean. Any questions? I think you guys saw something similar to this in 212, but that ALU was simpler. I think it only had 5 operations. This one's got 13. So most of these I think are pretty straightforward. I think you guys should be comfortable with bitwise and or not and XOR, right? So the idea is that you've got 2 32-bit numbers, and you're doing these logical operations between each of the 32 pairs of bits between A and B, and then the low output is where you're getting your result. Make sense? So for instance, if A is all zeros, then I could put anything in for B and tell it to do an and the result will always be 0, because if you and anything with 0, you get 0, right? Likewise, if I put all ones in for A, it doesn't matter what I put in for B, because if I put the op code as OR, then the result, and when I say result, I mean the low result, will be all ones. Everyone with me? Okay, so I think those are easy. Of course, add and subtract is nice and is easy. Multiply unsigned. The multiply unsigned, I didn't actually know this until I implemented this, but when you add or subtract, the result you get makes no difference if it's signed or unsigned. The only thing that the only difference between a signed and an unsigned add or subtract is how you interpret whether there was an overflow or not. Like overflow being that the result you got was out of range, right? It overflowed, it spilled over the upper limit or the lower limit. You guys make sense? You remember that? MIPS is actually, I think MIPS is the only architecture that I've seen that actually cares that much about overflows. Generally, like MIPS actually would generate an exception if you got an overflow. If you're running code on a MIPS processor and you do an add instruction, there's an overflow. If you're in Linux, you'll get a seg fault. It'll might not be say seg fault. It might say overflow exception or something. But the program will crash, right? It'll crash your code, which is why I don't know if you guys noticed this, but in 212 when you wrote code with a load or store and it got translated to a pseudo instruction, you would often see add u and sub u in there because those instructions were essentially ignore overflow, right? But most other architectures, Intel, ARM, I think RISC-V, they don't really care much about overflow, right? So they don't normally, you don't have to worry about whether you're doing assigned or unsigned, right? Sometimes they'll have a flag register that you can check, but generally speaking, it's not a big deal. Okay, so what about multiply then? Why do we care about multiply? Well, multiply, it does matter. You'll actually get a different result when you multiply two numbers, depending on, and when I say different result, I mean a different bit pattern in the result bits, depending on whether you're doing a signed or an unsigned multiply. Make sense? Right? So give me, let's...
Even if you multiply like two numbers that are both positive, whether you do a signed function versus an unsigned function?
Well, actually, no, that's not true. You're right. It's not always the case. But if you have, like, say, if you're multiplying two 4-bit numbers, and you have both numbers are 1, 1, 1, 1, that's a -1 if it's signed, and if it's a 15 if it's unsigned. So multiplying 15 times 15 is different from multiplying -1 times -1. You'll actually get a different result, right? So that's why we have two different multiplies. And then same thing with set less than. When you compare two numbers, obviously matters if they're, if you have signed or unsigned, right? Because a 1, 1, 1, 1 would be a -1 or a 15, right? Depending on whether it was signed or unsigned. So we have signed and unsigned versions of the comparisons. Okay.
Why are there two shift rights, or three shift rights?
There's a shift right, this is shift right logical, and there's a shift right arithmetic. There's two function codes. I think in this table, even though we have 13 operations, I have all 15 codes listed here. So there's some redundancy. So the shift right arithmetic has two function codes associated with it, meaning that the low order bit here is a don't care.
Okay.
And the reason for that is because if you look at the first two bits, if the first two bits are 0, 0, that means it's a logical operation. If the first two bits are 0, 1, it's it's a arithmetic, add, subtract, multiply. If it's 1, 0, it's a shift, and if it's a 1, 1, it's a compare. But there's only 3 shifts, and we have 4 codes, so there's an overlap there. Same thing with the comparison. There's 4 codes, but only 2 comparisons. So we have 3 different codes that all map to set less than unsigned. Someone else have a question? Okay. Okay, so let's talk a little bit about set less than. The idea, now the problem with set less than is that you're telling the ALU to compare two numbers and produce a binary result, but our ALU doesn't give a binary result. It gives a 32-bit or a 64-bit result, depending on whether you're looking at low or low and high. So the set less than will output, and this is in low, it'll output 31 zeros followed by either a 0 or 1 depending on whether A is less than B if you're doing a set less than. So just to refresh your memory, if you're doing a set less than signed, then the way that works internally is you look at the sign bits of the two inputs and also potentially look at the sign bit of the difference between A and B as well. So if A has a sign bit of 0, that means A is a positive number or 0. If the sign bit of B is a 1, that means it is negative, right? So if A is 0 or positive and B is negative, then the sign of the difference doesn't matter because you know that A must be greater than B, right? Guys with me? If A has got a 1 sign bit, it's negative, and if B has a 0 sign bit, it must be positive or 0, so that means that A must be less than B because it's negative and B is not. And then if they both have the same sign bit, then you have to look at the sign bit of the difference. So for instance, if you have 7 and 4 are the two numbers that come in, so both positive numbers, their sign bits will both be 0. So we're going to be looking at one of these two rows in the table. And so you'd subtract them. Now this subtraction, by the way, happens internally. This is like an internal signal, right? So the ALU is going to subtract them, but it's not necessarily going to expose this difference to the outside world, right? It's just going to do this internally and looks at the bit of the difference. And so if you subtract two positive or zero numbers and the sign bit of the result is 0, then A must be greater than or equal to B, right? So example is 7 and 4, 7 minus 4 is 3. So 7, 4, and 3 were all positive, so A was greater than or equal to B. And they could be equal too. Like if you have 7 minus 7 is 0, then you'll have the same sign bits. On the other hand, if A is less than B and you subtract them, if A is less than B and they're both positive and you subtract them, the result will be negative, and so that's corresponding to this row here. You guys with me? And then likewise, with negative numbers, if they're both negative, then you subtract and you get a positive result. That means that A is greater than or equal to, or not positive result, but positive or 0 result means A is greater than or equal to B. And likewise, if you subtract and you get a negative value, then A must be less than B, right? You guys remember? I think this is covered in 212. You remember that? Okay, so for unsigned numbers, it's less intuitive. With unsigned numbers, you still subtract. So you put two unsigned numbers in. Unsigned numbers are either 0 or positive, and you still subtract them. But in that case, you're looking for the carryout. Now you might say, well, what does the carryout have to do with this? Well, if you've got, like, say, 4 and 2, okay, now they'd both be positive numbers, 4 and 2. They get subtracted internally, and 4 is just, these are like a 4-bit version, 4-bit example. 4 would be 0, 1, 0, 0, and I would take 2, and in order to subtract it, I take the 2's complement of 2 and add. And if you do that, you get 2, right? So you add 0 and 0 and get 0, 1 and 0 and get 1, 1 and 1 and get 0 with a carry, 1 and 1 with a 0 and a carry, right? So the difference, is 4 minus 2, you get 2, no problem, but you get a carry out from that. And the carry out indicates that your result wasn't negative, right? In other words, you didn't sort of underflow the result in terms of the unsigned range. But on the other hand, if you have 2 and 4 and you subtract, so you take 2, you take the 2's complement of 4 and you add, you don't get a carryout. So you use the carryout to indicate whether the second number is greater than the first number, right? If the second number is greater than the first number and you subtract, you'll get a negative result, but you won't get a carryout internally in the subtraction. Yes?
When you say carryout, do you mean like an overflow bit?
Well, yeah, it's not really over. Carryout and overflow are a little different, but
Carryout when you move it around to the front and then add it back in again?
well, no, carryout is when you generate a carry out from the most significant column,
Okay.
right?
So they're both ones and then...
Right. So, well, in this case, what happened was, sorry, I should use this one because this one did not have a carry out. But if we look at this example, you add 0 plus 0 and get 0. 0 and 1, you get 1.
Yeah.
1 and 1 is a 0 with a carry, and that carry from bit 2 carried into bit 3,
Yeah.
which generated another carry, which would go into bit 4, which is just goes into the neither world, right? Because it gets carry out. But that's the flag you use to determine whether the result of that subtraction would have been negative.
Cause an extra bit, then you have carryout.
Then you have carry out.
From an overflow.
But that's good in this case, because in the case of unsigned numbers, when you subtract, you expect there to be a carry out if the result of the subtraction is greater than or equal to 0, right? So this is what you key off of to determine the set less than for unsigned. Okay, and then now you might say, well, why are you explaining all this? This is to understand. This is so you understand what's happening in the Verilog code inside the ALU. because we're going to be testing this sort of as a glass box. So you're going to be testing it knowing what's inside. You're going to be writing test cases. So so this is the way that the ALU is supposed to be determining those operations or calculating those operations. Okay, shifting. Shifting is, I think I mentioned shifts last lecture. So when you shift, and this is what your lab 1 code did. It did a bitwise shift, one bit per cycle. The MIPS instruction set, as do most modern instruction sets, include a barrel shifter, meaning that unlike what you did in lab 1, you can shift by an arbitrary number of bits, not just 1 bit at a time, but you could shift by, up to 31 bits. There's a 5-bit shift amount, so you can shift by 0 bits, or 1 bit, or 2 bits, all the way up to 31 bits. It wouldn't make any sense to shift by more than 31 bits, because then, you'd shift all the contents of your register out. But on the other hand, you could also argue that it doesn't make any sense to shift by 0 bits either, right? So you can shift by 0 bits, which doesn't make much sense because it doesn't do anything. But they won't let you shift by more than 31 bits because they only give you 35 bits for the shift amount. Okay, so logical shifting is when you shift. So this is the shift symbol in both in C and in Java and in Verilog. So this would mean I'm going to take this binary value and shift it 2 bits to the left. So meaning that the 2 rightmost bits get shifted away, right? So that 0, 1 goes away. I'm left with 1, 1, 0 on the right-hand side. And then on the left-hand side, I get zeros. Always get zeros because it's a logical shift. It shifts in zeros. Fills in the empty holes with zeros. You shift to the right, same thing happens. I'm sorry, if you shift to the left, the same thing happens, but you just go the opposite direction. And then arithmetic shifts are represented in Verilog with 3 greater than signs for right shift and 3 less than signs for left shift. I always forget to look this up. I don't think that works in C and Java. Phil, do you know? Is there an arithmetic shift in C or Java? I don't think there is.
In C, its arithmetic shift is how it's implemented by default for like right shifts.
Oh, no, that's right. No, in C, it depends on the type that you're shifting.
Yeah.
If you're shifting an unsigned, it does an unsigned. Yeah, that's right. I forgot. Yeah. So in C, that's right. I did look that up. Yeah, in C, the type of shift that's performed depends on the data type of the number you're shifting, right? Depends on how you declared it or how you typecast it. But in Verilog, they have explicit shifts for logical and arithmetic, right? And it makes sense because everything's just a logic in Verilog. Although there is a weird exception to that, and I'll show you that in a bit. So any questions about the shifting? Okay, so now one of the issues with shifting, by the way, is this is something that's a little arcane, but notice that we're telling Verilog to do a shift, and then we're just leaving it to the compiler as to how it implements that shift in hardware. Shifters are not necessarily trivial operations. Barrel shifters aren't anyway. Some embedded CPUs don't even have barrel shifters in them to save resources. You could design a shifter at a lower level in Verilog, by having if statements, and if the bit 3 of the shift amount is set to 1, then you shift by 8 positions, and then you check the next bit 2 is specified, you shift by 4 positions, and so on. You could create a stage shifter. In this case, though, we're just using the Verilog shift operation and then hoping that we get something, something good. And generally the case, in general you do. Same thing with add and multiply too. Like when you put add or multiply, you're basically telling the synthesizer to use whatever adder design or multiplier design it wants to use. But in some cases, you might want to have more control over that and design your own, especially for multipliers. There's a lot of ways to design a multiplier. And so that's what I got burned by the divider, by the way, when Josh asked that question, because when I put divide and just left it up to the synthesizer, it blew up. Okay. Okay, so let's get into the ALU then. So this is the ALU design, and we're going to give this to you. This ALU is actually, you can copy and paste it from the slides, but I would recommend that you get the version that's in the Lab 2 archive file, because when you copy and paste from slides, you get some artifacts, some non-printed characters, and the formatting is all screwed up. Not that, well, this formatting is screwed up anyway, because I've kind of compressed it for the slide. But anyway, so it's a module ALU. It has the input A and B operation code, shift amount, output, as I mentioned before, high and low, 32 bits. Output, there's a 0 flag. This is the diff. This is the difference between A and B. As I mentioned, it's is used for the comparison operations, and it's an internal signal. So it's a 32 down to 0, right? Meaning that it's 33 bits, because it's 32 down to 0. But that was done intentionally because I wanted to be able to preserve the carryout that we were talking about earlier. So I take A, which is 32 bits, but I use the curly brace to tack on a leading 0. And then I take B, and I do the 2's complement, right? So I take the 1's complement by doing tilde B. It complements each individual bit, and then I add 1, and that will give a 32-bit result. And if there's a carryout from this addition, it'll be lost, because notice that I put I tack on a 0 here as bit 32, right? So even if this addition generated a carryout, I'm still putting a 0 there. Okay, then, and that's because, you know, these are here only to preserve the carryout when I add the original values of A and the 2's complement of B.
That only happens for the smallest number, right? Like int min?
For what?
The carry out when you negate it and add one?
For the, I'm sorry, what was the question again?
The overflow only happens when you have the smallest possible 32-bit number.
Oh, you mean for the 2's complement? Oh, yeah, that's a good question. So if B is 0 and if I negate B and it's 0, then it'll be all 1s, and then I add 1 to it. So yeah, actually in that case you're right. If B were 0, then this add would generate a carry out, but I'm going to 0 it out anyway here when I create the 33-bit version of that number. Does that answer your question? I don't know if this is the best way. I wrote this myself. I don't know if this is the best way to go about this, to preserve the carryout. Preserve the carryout from a, subtraction, right? Okay, and then there's a 0 flag is set with an assign statement and a ternary operator. That's pretty straightforward. Then we have an always comb block. Now, why'd I use an always comb block? I could have just used a big nested ternary statement for this. I don't know. I don't remember what my rationale with that was, but the COM block allows me to use a case statement or an if then else construct. Whereas if I didn't put this in a COM block, I'd have this big, nested ternary operation. Now notice I put the default assignments at the beginning, high and low. This is something I recommended to you guys last lecture, and specifically, I think low will always be assigned no matter what happens after this. But high, I mentioned high only gets assigned when you do a multiply. So because I set high to 0 at the beginning, that allows me to guarantee that this always block will give me combinational logic because I'll be assigning all my outputs no matter what the data flow through the always block is. You guys with me? Now, I think I'm kind of new to system Verilog, but I think if I didn't put the high there and I didn't set the high, then it would give me a compiler error, right? Because I think the always comm guarantees that you write your behavior as combinational, and if you don't, if you forget to assign an output, then it will give you an error. Okay, so then I have a case Z on op, and then I just check out the op. Now notice I put underscores in here to separate the different operation families. Each family is denoted by the first 2 bits, the leftmost 2 bits, rather, the most significant 2 bits. So 0, 1 is my add, 0, 1, 0, 0 is my add, 0, 1, 0, 1 is the subtract, 0, 1, 1, 0 is the multiply, and 0, 1, 1, 1 is the multiply unsigned. Now this part's a little strange. I had to look this up. How to tell Verilog to do a signed versus an unsigned multiply. To do a signed multiply, you have to use this weird typecast where you tell it to interpret A and B as signed numbers. This is the only time I've ever used that before. And so by default, it does an unsigned. All right, so if you want to do a signed multiply, you have to use this syntax. Shifter is, as I mentioned, I just use the Verilog, whatever the built-in Verilog shift is for that. In response to Josh's question, that shift write arithmetic has 2 codes associated with it, which is why I have the question mark there. And then the comparison, I've got 2 comparison operators. Okay, so how do these work? The 1, 1, 0, 0 is the signed comparison, and I know that right away from looking at this because I'm looking at signed bits in this if statement, right? And if I was doing an unsigned compare, there would be no notion of signed bit. And then the 1, 1, don't care is the unsigned comparison. Everyone with me? Okay. And then the logical operations are the last ones to add here, and those are just the bitwise operators. And that's it. Pretty simple. It's pretty much just a bunch of operations all feeding into a 16-to-1 mux. Okay, so that'll be the ALU you're going to test in Lab 2, and then we're going to carry that forward and use that to start building up the parts we need for our CPU. We're going to be doing a bottom-up type design construction of the CPU. So let's talk about simulation for a minute. Lab 1 was a little, you probably noticed it was a little trial and error because you try something, you put on the FPGA, and either works or it doesn't. If it doesn't work, you really don't know what to do next because it doesn't work. So just randomly try something else and see if you can make it work. Obviously, there's a better way to go about this, and that's you can do simulation where you are running the code on essentially a virtual FPGA, right? It runs it through a discrete event simulator. So the one we use in class is called ModelSim, and it's kind of nice. This is a commercial tool. This is an industry standard tool. You could talk to anyone that works in chip design anywhere in the world, and they'll all know what ModelSim is. It's universally recognized as the best behavioral simulation tool ever. Synopsys has one that is roughly, considered to be almost as good, but ModelSim is always kind of the de facto standard for this. So there's ModelSim is kind of not very user friendly though, to say the least. So I'm going to see if I could do a little demo of this. So here I'm in a bash shell, and I've got some system Verilog files here. I've got this thing called sillyfunction.sv, and I'll open that to show you what's in there. So silly function is, hopefully you can read that. Is there a, View. Terminal zoom. Does that work? Oh yeah. All right. Terminal. Okay. View terminal zoom. Okay, make that a little bigger. The silly function is real simple. It's got A, B, C inputs, just 1 bit, output Y, 1 bit, and just has an assign statement. It's just a Boolean expression. So before you can simulate this, you have to compile it into a proprietary binary format that's recognized by ModelSim. The command to do that is vlog and the name of the module. And you can also, you can specify more than one file. You can use wildcard. So if you want to compile everything, all the system verilog files in your directory, you can say vlog star.sv, for instance. Now you want to check though, if you compile more than one file at a time, you want to, it's going to print out a report for each one separately. And so if you compile a lot of files, you may have an error in one of the files that scrolls off your terminal. So be careful with that. But this one I had 0 errors, 0 warnings. When you compile it, it creates a directory in whatever directory you were in when you compiled it called work. That work is your library. So everything you compile by default goes into a library called work. You guys with me? If you go in the work, I don't know what any of that is. It's all proprietary stuff. Okay. So once you've got that in there, you can simulate it. You could type vsim space silly function. In this case, I'm going to just say silly function without the .sv because I'm simulating the module. Now, at some point, ModelSim started doing this thing where it optimizes out stuff it doesn't think is important in your design. I don't know why, but when that happens, you can't see what's going on. So we tell everyone in this class to use the v no opt switch. Is it v no opt or no v opt? No v opt, right? Hold on, it's in the slide. I forgot, brain fart. No v opt. Yeah, that's right. No v opt. No v opt. PT spelled out. No v opt. Okay. vsim dash no v opt, silly function. And that's going to pop up a window, GUI window, hopefully. There it is. Okay. So, this is this little pane that's labeled, well, it says sim. This is what I call the structure pane, because this shows you the design hierarchy. So if I had any modules that were instantiated under the silly function, they would show up here and I would be able to drill into them. But this is a flat module, so I can't do that. So as you might imagine, you have to compile all of the modules that make up a design, but when you run vsim, you're only running it on the top level module, whatever you want to select as your top level module, your most abstract module. That would be the root of your design hierarchy. So that shows that. This is the objects pane that shows the internal signals as well as the inputs and outputs of whatever your current scope is, and your scope is defined by whatever you click on over here in your structure. Well, so I only have one scope because I only have one module. And then this is the command line interface. And when you start ModelSim, you also get this wave window that comes up automatically as well. So if you want to add stuff to, generally speaking, the way you use this is when you start simulating, you have to add signals to the wave window that you want to monitor, that you want to see. So I'm going to highlight my A, B, C, and Y. I'm going to do a right click and say add wave, and then they show up in the wave window here. And then you'll notice that they're labeled with their fully qualified hierarchical name here. So, silly function ABC, Y. If you had other signals that were lower in the design hierarchy, you would have more prefixes here indicating where they appear in the hierarchy, which can get cumbersome. But if you hit this little black button in the lower left-hand corner, it'll turn off the prefixes, so it'll just show the raw names. And then there's a button right here that says run, and you can hit run. And you can run it. I hit it a bunch of times. It's running for 100 nanoseconds at a time as indicated there. And if I hit the little zoom button, it'll zoom in and show me what's going on. And as you can see, this is just a flat line. Nothing's going on. Notice I have, excuse me, I have 3 blue flat lines and 1 red flat line. What do these mean? Blue indicates Z, high impedance. Remember we talked about that last time. Z is just floating, it's not being driven by anything. Red is undefined because my Boolean function generates an undefined value when it reads in floating inputs, right? Because logic gates don't know what to do with floating inputs, right? So that's why I got X. If I want to actually make it do something, I have to stimulate the inputs somehow. I have to provide a stimulus, which you can do through tickle commands. So ModelSim uses a tickle interface. Now you can also do it through the GUI too. You could do a right click on A and say, sorry, I don't want to go in the, yeah. If you go in the wave window and right click on A, I can force it to be, say, a 1. Now nothing happens until I have to run it after I forced it. So the simulation is always at a certain state. It's always at a certain time. And you'll notice that it says down here, it says, right now my simulation time is 1900 nanoseconds. And I set A right there at 1700 nanoseconds, right? And that's where A went from being a Z to a 1. But because I still have 2 undefines going in the logic function, I'm still getting a red output. So I can also force B and C. So force B to be 1, force C to be 0. Whoops. Force C to be 0, and then I can run, or I can type run 200. It'll run it for 200 nanoseconds. And you can see there that it was at 1900 nanoseconds that I forced B and C, and once I had all 3 inputs to my function, then that Verilog module was able to force the output to be 0. You guys with me? So you can test modules this way. You can write a script that puts forces and runs. Force run, force run, force run, force run, and then you can run the simulation and you can watch what's going on here. But as you might imagine, that's a horrible way to do it. Very tedious. You don't want to do this. You don't want to test things like this. The solution here is to use a test bench. A test bench is a Verilog or system Verilog module that you write that provides not only the input stimulus for the design you're testing, but also it can check the output to verify that the output you're getting is what you expect to get from a properly working module. You guys with me? So the test bench is a harness that goes around the design you want to. So in this case, silly function is what I want to test. I want to know if it's working. To tell if it's working, I could, run commands in ModelSim and visually inspect the output, or you write a test bench which will systematically go through different test cases, and it will also check the output. And if there's a mismatch between what you expect to get and what you are getting, then it can raise an error. So that way, I can run these test vectors, which are individual test cases, against this module, and I don't have to sit here and just. The only time you have to look at these waveforms is when you're debugging, right? If you're debugging, if you have an error and you want to figure out why do I have an error, then you can look at the waveforms for the purpose of debugging your design. But you don't want to have to look at these to determine whether your design is working. That's horrible. Tedious. Guys with me? Okay, so that's what a test bench is. System Verilog was designed as was the premise of System Verilog is that it has more testing functionality in it than Verilog did. So this is, this notion of designing test benches is important. Now, one thing you got to keep in mind, I think I briefly mentioned this last lecture, but not all Verilog code that you write is synthesizable. So there are certain things that when you put into your code, it's like a poison pill. It will prevent that code from ever being converted into hardware, like on an FPGA, for instance, or an ASIC. Now you might say, why would anyone do that? Well, the Testbenches is the reason. The Testbench is not designed to be put into hardware. The Testbench is only designed for simulation. So you can use features of System Verilog in your Testbench that are designed for testing and simulation, but not designed to go into hardware, right? So to design your testing is supposed to be all synthesizable Verilog, something that could go into hardware. Your Testbench is this magical thing that can only be run in a simulator, right? Because you can put things in there like, delay for a number of time units, or you can put print statements, that kind of stuff that can't be converted to hardware, okay? All right, so let's look at some examples here. Oh, also, I'll quickly mention that in ModelSim, most things you can do in the command line interface have a way to do it through the GUI. So now you'll notice that we tend to favor the command line interface, and it's not because we're trying to be snobs, but the GUI is really horrible. I mean, it's written. I don't know what it's written in. I think it's written in TK or something. It's horrible. It's really lousy. You'll notice, like for example, if you want to compile through the GUI. Now, I compiled really easy. I just type vlog space file name. But if you want to compile through the GUI, you can go. There's a compile pull-down menu. It brings up this really crappy looking thing, and then you highlight the files you want to compile, and you hit compile, but that doesn't make this window go away. It just hangs out until you hit done. So you have to hit compile, then you have to hit done. But the problem is that any kind of error messages you get from your compile from these individual files are going to be behind this window on the command line window, which you might not even see because this thing is covering it. So that's why it's better to use the command line interface for this stuff. But like I said, instead of forcing, you can right-click on a signal in the wave and say force, or you can just type force, right? Same thing with, the only time I like to use the GUI is when I'm running. When I'm trying to step through, like running, there's a little run button that'll advance the simulation. I like to use that. And there's a reset button too. I didn't show you that. So if you go over here, these are the run buttons. You could type in a different number if you want to run for longer. But this is a restart button. And so the restart button restarts the simulation, but it also reloads any files that you've changed and recompiled. So if you're trying to debug something and you're making changes, then you're going to want to restart often. Okay. Okay. Okay, so I think I explained all this already. Testbenches are HDL code that tests another module. Generally not synthesizable, meaning that they're just designed for simulation, and once you use them to validate your design, you kind of just throw those away, throw the Testbenches away, and then you take your design under test and you actually ship that out to customers. Now, here's the problem with Testbenches. I spent the better part of today debating this with Charles. There's no one way to do a Testbench, right? It's all up to your individual style. There's a lot of ways you can write a Testbench. It's really open-ended, right? It's not like there's a specific template that you have to use. There's not. In the slides, I'm going to present to you the Testbench designs that are in the book. And I'll also show you the one that we wrote for you to help you to get you started with Lab 2. Okay, and they're a little different. Okay, so let's start out with the silly function. This is the same silly function I showed you before. Here's a very simple test bench that will drive the inputs to silly function, but it doesn't check the outputs. It's not a self-checking test bench. So the first thing you'll notice in this design is I have module test bench 1. Notice that there's no inputs or outputs to it, which is intentional. Test benches generally don't have any I/O because they're self-contained, right? They operate by themselves. They're like self-sufficient. In this case, I've got these A, B, C, and Y are declared as logics because they're the wires that I want to connect to the silly function, which is my design that I'm testing, right? You might say, why do you have those on 2 separate lines of code? I don't know. No reason. I could have declared them all on their own line. Silly function is instantiated here. I call it DUT, which stands for Design Under Test. Remember, though, I mentioned to you that this name is meaningless. The only time you'll see this is in the simulation, which I guess makes sense because this is meant to be simulated. I used the other style. I forgot to fix that. Okay, so notice when I instantiate this, I connect A, B, C, and Y to it, but I do it. I've been trying to change all this. I do it through the order, right? As opposed to putting the other notation dot A open parenthesis A close parenthesis. This syntax works in Verilog, but I don't think it's good. It's hard to match up the actual arguments to the formal arguments based on their order, especially if you have a whole lot of them. But
so it can be interpreted ambiguously potentially if the dot parentheses isn't used. Is that what you're saying?
well, if you don't use the dot format when you connect the ports of the module, then it relies entirely on the order. So it's going to match up the connections here that correspond to the ordering that they're listed in the module line. But the problem is someone might change that ordering. You could change that ordering in here, and then you just broken your instantiation. So, and also, a lot of modules have a lot of inputs and outputs, and it's really hard to figure. It's like, okay, it's the 13th input, so I have to count 1, 2, 3. It's like it's really, you don't want to do it that way. It makes the code unreadable. This originally came from the book, though, and they still have some I think bad stylistic choices in their code. Okay, so I instantiated, and then in this case I have nothing else in here but an initial block. And the initial block sets the inputs, and it follows each of the settings, each of the test cases with a hash mark, pound sign, I don't know what you call it, whatever that is, hash 10. That is what makes this unsynthesizable. I've just disqualified this from ever being converted into hardware.
What's the hash 10 do?
It puts a 10 time unit delay in the simulation. So here's the, now wait, let me back up here a minute. What do I mean by 10 time units? Yeah, it's whatever's specified. Notice in this case it's nanoseconds, but you can change that. And that brings me to another important point. In behavioral simulation, all logic has a delay of epsilon, meaning that all logic, no matter what it does, will propagate inputs to outputs within an infinitesimally small, non-zero amount of time, right? What that means is that there's no actual logic delays, but if I set inputs and I want to see the resulting output from combinational logic, I have to put some delay. It doesn't matter what it is. So you'll notice that in the test bench that we give you, Charles likes to put 1 here, right? He just puts 1. I like to put, in the book, we like to put 10, right? But it doesn't really matter because the actual time scale of the simulation is irrelevant. The only thing that matters is that you have to put some non-zero amount of delay if you want to see the combinational logic respond to these inputs, right? So I'm going to set A, B, and C here, and then I put some delay, and then I'm going to look at the output. Yes?
Is that how we get the slope on the transitions, or would it just be a straight?
No, it's still a straight line.
Okay.
Yeah, in fact, you'll notice I already showed you this with my little demo here. So when I was in Model Sim, and I type force A to be 1, I can actually do force A, force B equals 1, force C equals 0. Whoops, force C equals 0. And then over here in the wave window, nothing happened. Right? I won't see anything happen until I run it for some non-zero amount of time.
Okay.
So I can put anything I want up here. I can put like just 1 here and run it for 1. Now notice that there is a labeled x-axis here that is in units of time, but the actual amount of time is really kind of meaningless because we're only simulating the behavior, not the actual technology-dependent delays, right? Okay? So let me zoom in here a bit so you can see what's going on. So this is so small. If I zoom in, now look, the x-axis just got obliterated because I zoomed all the way into 0 to 2 is my scale, and then you can see the values I set. The point though is I had to force and then I had to run in order to see the result of what I forced. But the amount of time I ran for was irrelevant. Yes?
Does it actually run for that amount of time, or does it simulate running for that amount of time? Like the 1 nanosecond Theo put in, does it actually run for 1 nanosecond, or does it simulate running for, like if we put like 10 seconds, would it actually take 10 seconds to get the whole?
Oh no, it'd take longer than that because it doesn't simulate in real time. It takes much longer to, which is why, by the way, like if you wanted to do a really long test, like they used to do at Intel here at time when in town on St. Andrews, they would do test benches in simulation, but when they wanted to do a longer one, they'd actually have to take the circuit and put it in actual hardware and then use a physical device to hit it with test vectors. So that way it would be going in real time. This is far from being real time. Okay, back to here. Okay, so what does this test bench do? It does nothing but stimulate the inputs, and then the expectation is that I have to open the waveform and validate that they're working with my eyeballs. This version is a little different. This one adds the checking to it as well. So this one, oh wait, one other thing I want to mention, I forgot, sorry, back up. Back here, notice I set A, B, and C, and then I delay, and then I only set C. Right? Why did I not set A, B, and C? Because I wanted, this is going through a counting sequence. I'm going from 0 to 7. I'm treating A, B, and C as the little 3 bits of the counter. So after I set them to 0 and I delay, I only set the least significant bit to 1 and then delay because it retains the value of A and B, which were both 0. Then I go to the next one and I have to change B and C, but I keep A what it previously was. Right? Okay, over here I do the same thing, but now I have got an if statement after each one of these delays. I have an if where I check y, which is the output of my silly function, to check to see if it equals what I expect it to equal based on some idealized golden, ground truth, gold standard, whatever, the way it should be behaving, right? And if it doesn't match, then I print a message saying that test case failed, right? So the whole idea is comparing what you get versus what you expect to get. And if that comparison is not true, then you have to indicate that to the user, and then the user would then have to debug. So then you have to start drilling down and inspecting and trying to figure out. You have to start doing some diagnosis. But if everything works, you should just be able to run this test bench and it'll check out and you don't have to worry about it. Now, one thing I want to point out here, notice this says bang equals equals, right? That's a strange operator. In fact, that operator was not in the table I gave you in the last lecture. Right? I gave you a table of operator precedence. That wasn't listed. It was bang equals is not equal. This is another non-synthesizable aspect of Verilog or system Verilog. If you use equals equals or bang equals, standing for equals or not equals, that will fail if what you're comparing to is an x or a z, right? If you have one of those values that's not 0 or 1, it'll always fail. Even if you're comparing x to x, it'll still fail. Why? Because in reality, you cannot compare x to x. There's no way to design hardware that'll compare two undefined values. But sometimes when you're simulating in a test bench, you do want to be able to compare if two values are both x's. Why? Well, you'll see in the test bench that we give you, we use that to figure out when you're done with all your tests. We have a little test vector file, and once you hit an x, you're done, right? So this is something you'll see in test benches, but not in synthesizable code. Okay, so now what's the problem with this? Why is this limiting? This is limiting because you have to manually type in all your test cases in Verilog. You have to encode all your tests in Verilog. Who wants to do that? It would be better if we could have a separate file with all the test cases in it, right? And then the test bench will just run that file, right? We want to separate the behavior of the test bench from the actual cases that we want to test. And that's usually how people design test benches. They have a test bench, and then they have another file that contains test vectors that the test bench reads. Now you might say, wait a second, you're telling me that you can write Verilog code that reads a file from a disk? Yeah, but again, only non-synthesizable, right? That's test benches are in Verilog, but they look like sequential code, like Java code, right? They look like a script, right? Yes?
Is there a reason to write them in Verilog instead of like Bash or C or something?
That's a good question. I mean, Verilog, everything's integrated, everything's kind of under one umbrella inside in the simulator. I mean, you could write in Tickle. Charles actually advocated for writing everything in Tickle,
Right.
which would basically mean that you would write a script for Model Sim to run through all these things. But then we have to teach Tickle. This way, you're just using one programming language.
It seems almost like two different ones. One's that's synthesizable and one that's not.
Well, there's been a lot of languages people have written specifically for testing. They used to teach one when I was in grad school in the verification course. It was called, no, I don't remember what it's called now. It was called like I or something, I forget. But it was a whole language that was designed just for writing test benches. But usually those things, they come and they go, but Verilog and VHDL sort of just always persist.
Okay.
So they call those, verification languages. Yes?
My question was a little bit tangential. Has USC ever offered a verification course?
No.
Okay.
No, they had one at Pitt when I was in grad school in the late 90s, early 2000s, and they were teaching that language specifically. And that course, the projects in that course were the students would get a kind of a black box module that they couldn't see the code for, and then the projects were to find bugs. So sort of write test benches that find bugs. And in fact, that's what this lab 2 is going to be, but we're going to give you the code. So you're going to be testing the ALU. So it's a little bit easier because you can use, you can see what's in the ALU. You can design your test cases around the contents of the ALU, as opposed to getting an opaque module. Yes?
Last question, I promise.
Sure.
Does Verilog have like property-based testing frameworks, or would you have to write that from scratch?
Oh my lord.
I'm sure it does. I would guess it either does or there's libraries that do support that. There's something called Open Verification Library that's like that does like where you write implications as opposed to actual test vectors, and that way it randomly generates it, and then it looks for you write implications instead of vectors. So you can encode your intended behavior as a set of logical implications, and then you just let the test bench run by itself, and it just hits it with all these random vectors. I'm a little bit afraid of those though, because even with this ALU, even if you just look at A and B alone, that's 64 bits. There's 2 to the 64th power possible inputs to that thing, which if you ran that even at 50 megahertz, it'd probably take longer than the age of the universe to finish all those. So it's not really, random generation of test vectors is, I don't know, you may not hit all the, corner cases. It's a little risky. So. Okay, so the book, now here's where things are going to diverge a little bit. So I'm going to try to, hopefully I don't confuse you guys with this part. The book's idealized test bench generates a clock signal. Now, why do we need a clock if the ALU is a combinational logic circuit? They use the clock only to separate the driving of the inputs to the checking of the outputs. Now, you might say, well, wait a second, it did that in the old one. The old test bench had that. It just used this hash symbol, right? Yeah, the book decided at some point the hash symbol wasn't a good way to go about this. So they use a clock. I think the reason they did this is because once you guys start writing test benches to test sequential logic, then you're not following that same methodology where you're waiting for a fixed amount of time. You usually have to wait in units of clock cycles, right? Like for example, the pipeline CPU, you give it an instruction and you have to wait 5 clock cycles before you can expect an output. So I think this is a better way to go about it. So you generate a clock signal. On the rising edge of the clock, you hit the ALU with an input, a new test vector. And on the falling edge of the clock, you look at the output of the ALU or whatever you're testing, and you check to see if it matches what you expect. The fact that you're looking at it on the negative edge, the falling edge, forces there to be this time difference between the input and the output. You guys with me? Now I mentioned that logic is instantaneous. I don't know if instantaneous is the right word though. Instantaneous kind of implies 0 time. All logic takes time, but a trivial amount of time. You guys with me? So you have to run it for some amount of time, but as long as that amount of time is more than 0, then it propagates, okay? Okay. And, as I mentioned, we have this test vector file. This is something else that is completely up to you how you structure these things. But in this simple example, we have binary test vectors. Each test vector is a 4-bit value. Now, there's one per line, and the assumption here is that each line represents one test, which is done in one cycle, one clock cycle. The 4 bits, the most significant 3 bits represent the inputs, and the least significant bit represents the expected output. So in other words, that's a truth table. This is literally just the truth table of that Boolean function. I look at all 8 of my input combinations. Okay, so the test bench gets a little bit more complicated, but it only looks that way because I've got it on slides. Once you have this in, like a text editor, it's not as intimidating. But the idea is I declare a clock and a reset. I've got A, B, C, Y expected, and Y. Y is the actual Y. Y is what I expect it to be. Then I've got a counter for the vector number and the errors. I don't want to bail out as soon as I get an error. I want to count the number of errors. And then I have this thing called test vectors. Now this is a new syntax. I mentioned to you guys last time that Verilog puts array bounds before the name of the signal when you're declaring it. Right? So you say, logic 31 down to 0 vector num. What does that mean? Well, vector num is a 32-bit signal. But notice here, I've got test vectors. I've got 3 down to 0 because that's the width of each test vector. But then I've got this additional thing after it that says 10,000 down to 0. This is the depth. So in Verilog, when you have a 2-dimensional array, the width goes first. It appears before the name of the signal when you declare it. And the depth appears after the name. Why is that? I don't know. That's, to me, it's always, I think that's strange syntax, but just keep in mind that the width is first and the depth is second, which is opposite of the way Java and C work. But which, the Java C, they always have the depth and then the width, right? With two-dimensional arrays, the depth is first, the width is second. Okay? So then I instantiate the silly function as my design under test, and this time I used the proper syntax for wiring that up. Then I have an always block. The always sets clock to 1, it delays 5 units, it sets clock to 0, it delays 5 units, and then it ends. But because this is an always block with no sensitivity list, it runs infinitely. This is the only time that we're going to be using just always without a, remember I told you that you should have always comb or always flip-flop. This is just an always. And then I have an initial block where I use this function. Functions in Verilog start with, or I should say built-in functions in Verilog, start with a $sign. So you do read mem b, you specify the test vector file and where you want to write that into. That will take whatever's in this test vector file, which is the one I showed you, and it will use that to initialize the test vector's 2D array, or RAM. And then it will initialize the vector num and the errors, and it will also have this reset that will set to 1, wait for 27 time units, and set it to 0. Now, if you were testing any kind of sequential logic, you'd want there to be a reset pulse at the beginning that would reset all your registers and flip-flops. Everyone with me? So far I showed you an always that just drives the clock, and the initial that initializes stuff, right? Okay, then we have two always blocks come next. We got one that activates on the positive edge of the clock that reads a test vector out and drives it onto A, B, C, and Y expected. Right? So rising edge of the clock, I hit the ALU, or in this case the design under test, with inputs. And then on the falling edge of the clock, which is always at neg edge clock, I check to see if Y doesn't equal Y expected, and if it doesn't, I print an error and increment my error counter. Now there's some other details in there I'm skipping over, but I'm just trying to highlight the important parts here.
So
Yes?
is this synchronous? Is this always will this always finish before the next clock rise?
Yeah. Yeah, so because it's a clock signal, then the negative edge will happen before the next rising edge. So we're going to check the outputs before we change them. Next rising edge.
Right, but the display could take a few milliseconds to print the console or something like that.
Oh,
This is simulated time.
yeah, it's simulated time. Yeah, that's right. Yeah,
So this is in the simulator.
yeah, that's right. Okay. Yeah, actually, when you start Model Sim, you can actually set whether it's running on picoseconds or nanoseconds, and so, depending on how you set up the simulator, those delays might mean different things. Missed it. Yeah. So this clock, this has a 10 time unit period, but that 10, that could be 10 nanoseconds or picoseconds. It's kind of artificial. Okay, okay, and this was the other thing I alluded to earlier. When the test vector, notice I declared test vectors as having, 10,001 depth? Yeah, I declared it with 10,001 depth, but the actual file only has 8 lines in it. So, line number, the 9th line all the way up to the 10,000 in first line will just be populated with don't knows, X's, right? So I have some code in there that stops the test bench once I hit an X, meaning I've gone past the edge of my test vectors, at which point I just print a message saying how many tests have completed and how many errors. And there's a special thing here called $finish that ends the simulation. Okay. Notice that there's a display function which looks a lot like printf in C or C++. It's got a way to do formatted printing. So in this case, I put %d, that's a decimal number. So it's going to take the vector num and print that as a decimal number, right? On the other hand, when you have an error message, like here, when I say error inputs, there's a %b, which is binary. And in this case, I'm taking A, B, and C and concatenating them and printing those concatenated value as that binary value. So it'll say like 0, 1, 0, for instance. You guys with me? Anyone not familiar with formatted printing? So in CSCE 240, you guys use cout, right? And of course, Java has the print line.
That's printf too, actually, just no one uses it.
Okay. Yeah, if you have trouble with this, let me know. If you're not sure about how this formatting stuff works. Okay. Okay, so that's the books test bench. Now I'm going to show you one more. I'm sorry, this might be a little gratuitous, but this is now test bench number 4 is the one that Charles and I wrote a few semesters back. This one is very similar to the one I showed you, but it's been sort of simplified. Instead of having a clock that is used to synchronize the tests and the inputs and the outputs, this one uses a for loop. So this is more similar. You guys, I'm sure you'll all actually be more comfortable with this type, because this one just has a for loop that walks through the test vectors. It still has the delay. So this delay is used to separate the driving of the inputs and the checking of the outputs, right? Which Charles just has, he put a 1 in there, which means in Model Sim, if you're looking at the waveform, you might have to zoom in to see that. But it works. It works just like the other one does. It just doesn't have a clock. When you guys test your CPU, though, you're going to have the clock in there because the CPU requires a clock to run. Okay. So that's why I left, both versions up here in the slides. Okay. Any questions about that? Okay. So that is all you need to know, hopefully, for Lab 2. I want to run through that really quick. I think the TAs will also go through this in lab, but just to check to see if you have any questions. The objective of the lab is to develop a set of test vectors. So we're going to give you the ALU, and we're going to give you most of the test bench, some of the test bench as a skeleton. So your job is going to be to finish the test bench and write test vectors for the ALU. Right, test vectors being, a set of inputs and the corresponding output. The ALU that we're giving you has at least one bug in it. Possibly more. When I first wrote that ALU, I didn't know it had a bug in it. We used it for a while before we even realized it, but there is a bug in there. We left it in there because this is a good opportunity for you to find the bug. So there is a test case, and when I say bug, what I mean is there is a set of inputs you can give the ALU where the ALU will not behave properly as defined in the table of ALU operations. So for instance, opcode 0100 is supposed to add A and B and put the result on low. And there may be a case where you do that and you don't get the proper sum, for instance, of A plus B, right? So your job is going to be to write the test bench and write your test bench and your test vectors thoroughly enough to discover this bug, okay? And to validate that the ALU, whether the ALU is working and under what conditions it doesn't. Okay, I probably don't need to go into too many more details. One thing I want to mention is the test. So we have a test vector format for you. I mentioned in the lecture that this is kind of up to the individual, tester. There's no one way to do this. But for this lab, we're going to give you a format for the test vector so we could use your test vectors with our test bench to test the ALU. So this is a 148-bit signal. The test vector is comprised of 148 bits. That sounds like a lot, but think about it. A, B, low, and high alone are 32 bits times 4, right? So that's 128 bits right there. And then the other bits are things like the shift amount, the op, 0, and we've got this marker here that's kind of a dummy, but we're going to use the marker to determine whether you've hit the last test vector or not. So the marker is just supposed to be 4 1 bits for each of the test vectors. Everyone with me? Okay. So that's, the other thing too, one other thing. The test vectors, the one I showed you was written in binary. So the example I showed you was, these are binary, right? And which is why if you look at the code that reads that is readmem-B, readmem binary. For the 148-bit test vectors, obviously you don't want to write those in binary, you're going to be writing them in hex. And there's another function called readmem-H that is works the same way, but it expects a hex file. So if you look at the assignment sheet, the lab sheet, it has width in bits and width in hex digits, right? Which is just width in hex digits, number width in bits divided by 4. Now shift amount is 5 bits. 5 is not divisible by 4. So in the test vector, we're going to allocate 8 bits for the shift amount, even though we only use 5 of them, right? Likewise, 0 is only 1 bit, but we'll just allocate 4 bits, 1 hex digit, right? So some of the bits in the test vector are don't cares. Any questions about that? Okay, and this will be due in 2 weeks, September 27th. One other thing I want to mention. So you're going to be turning in a report with this. The report is going to have your test vectors that are labeled with comments. And we also want a little write-up where you describe why you feel your test vectors are adequate and also what the bug is, how you found the bug. Hopefully you find the bug. Okay, the TAs that's posted online and on Dropbox, and the TAs will also go through this as well with you in the lab section. So that's why I kind of blew through it. Okay, next thing I want to talk about is the timing. So I mentioned that the simulator is a behavioral simulator. It's a functional simulator. It does not simulate the actual circuit delays. The reason is because it can't, because the circuit delays are depend on the technology. The circuit delays that you would have in an ASIC, for instance, like if you made a chip, are going to be much less than what they are on an FPGA. Because FPGAs are reconfigurable, you pay a huge overhead for that reconfigurability, meaning that the wires and the gates are bigger than they would be on an ASIC, and thus they have more capacitance. And that's really what determines the delay, is capacitance. When you charge a capacitor, there's a constant. The resistance times the capacitance is the amount of time it takes to charge up that capacitor. So in a logic gate, you have a lot of capacitance. You've got capacitance on the gate, on the input. There's capacitance, because that's how MOSFET transistors are actually capacitors. They work by the gate of the transistors is a capacitor between the gate and the channel. It acts as a capacitor. And the capacitor is what attracts the minority charge carriers in the substrate, in the channel. And that's how you can turn on the transistor or turn it off. So these are fundamentally, they have capacitance in the input. And then the output, the wires themselves that form the output, also have capacitance. Likewise, they have resistance because they're not superconductors. So there's always going to be a delay between, like even something simple like this buffer. there's going to be delay between when you change the input in a way that would change the resulting output state. There's going to be delay there. Are you guys with me? Now, like I said, the simulator ignores this delay because we're only interested in the behavior. We're not interested in the logic timing resulting from having synthesized it. Make sense? You guys with me? Okay. So there's actually two kinds of delay that you have to be concerned with. There's propagation delay and contamination delay. Propagation delay is how long it takes for the output to settle, for it to go into its final state after you change an input. So the propagation delay is really just the speed of the gate, the logic gate, think of it, because it's the amount of time you have to wait to ensure that you've reached the final output value. The contamination delay is the minimum amount of delay before you'll see any change to the output. That makes sense? Now, you might say, why would there be a difference like for a single gate? Well, usually for a single gate, there's not, but these concepts are being applied to logic circuits. So you'll have a logic circuit, and a logic circuit will generally have different paths through the circuit. For example, this circuit. Notice how I've got, now, by the way, you guys are used to doing the, canonical sort of product of sums and sum of products that generally always have two logic levels, right? But in synthesized circuits, you don't have that. You'll get circuits that are not always two levels. In this case, I've got 3 levels deep of gates that I have on my critical path, which is the worst case path. But there's also another path from D to the output that only goes through one gate. You guys with me? So there are some paths through the logic circuit that are longer than others depending on which input you're changing. Make sense? So the contamination delay is essentially how long it takes to get through the shortest path, and the propagation delay is how long it takes to get through the longest path. Does that make sense? So that's why you see TPD, that's the propagation delay, and TCD is the contamination delay. And in this case, they're measured in terms of the individual propagation delays, as well as, in this case, the contamination delay is the contamination delay of the individual gate.
So when you say contamination, that's like the shortest path?
Shortest path, yeah, through the circuit or through, in this case, it's also, you have a contamination delay associated with each gate as well. Make sense? Okay. Okay, I mentioned that. Okay, so this also introduces this idea of glitches. Did you guys talk about glitches in 211? Okay, a glitch is when you can change an input on a logic circuit, and the output will change more than once. You'll get a glitch. Like you'll change an input and you'll see a spike in the output that's momentary. And the funny thing about glitches is that you're going to actually see these in model sim. And you might say, well, wait a minute, you're saying glitches depend on the delays, which is technology dependent. Model sim doesn't model that. So why does model sim show glitches? I was never clear on how it determines whether there's a glitch. It has to do with unbalanced logic, but every once in a while you'll see a glitch and you'll see like a spike in model sim, but you don't have to do anything about it. Because we're assuming that when we get our circuit out of the Quartus, it will guarantee timing for a certain clock period, right? And so as long as you have timing guarantees, then any glitches that happen would happen within a clock cycle, and thus would be ignored because things only move on the clock cycle, right? Each clock cycle in a sequential circuit. You guys with me? So specifically, why do glitches happen? Well, the book has a neat example of that. So if you have a circuit that looks like this, and you change, so you have A as 0, B as 1, and C as 1, your output will be 1. And the idea is that A and B are both 0, they get inverted, or I should say complemented. They go into this AND gate. The AND gate will have a, actually, initially B and C are both 1, which go into this AND gate, produce a 1, and then that 1 goes in the OR gate and gives you a 1, right? So we have a 1 coming out of this AND gate, and because it goes in an OR gate, it doesn't matter what the other input is, right? But if you change B from 1 to 0, the effect of that is that it'll activate the top AND gate and deactivate the bottom AND gate at the same time, right? Except it doesn't happen at the same time because of these extra inverters you have to go through. So what will end up happening is that the bottom AND gate will get deactivated before the top AND gate gets activated because you have to go through this extra level of logic. And so you'll end up with a glitch where the output will be 1, it'll go to 0, and it'll come back up to 1. Right? Because there's a delay between these two AND gates when they activate. Right? That's the glitch. Now, if you look at it logically, if you look at this on a Carnot map, what's really happening there is you've got these two groupings on the Carnot map, and when you change A, was it A or B? B. When you change B from 0 to 1, so you start out here on the Carnot map, you change B and you go from here to here. You leave one grouping and you go into another grouping on the Carnot map, right? If you add an extra gate that covers this commonality, that bridges these two groupings on the Carnot map, it actually fixes the glitch because it keeps you within one grouping as you transition from this state to this one. So you can add that extra, if you needed to stop the glitch, that would be a way to fix that. So the book, these are the book's comments on glitches. They don't necessarily cause problems because of synchronous design conventions. What that means is that in a synchronous design convention, we'll talk about that in the next chapter, in the next lecture, next week. You design your circuit so all the propagation and all the glitches are done before the next clock edge, right? So you enforce timing, you enforce setup and hold time in your sequential circuit, synchronous circuit. But it's important to recognize a glitch, and you'll see it on like I said, you'll see it in model sim and on an oscilloscope if we were using one. And sometimes you can't get rid of all glitches. Okay, any questions about this stuff? So the contamination delay and the propagation delay is a topic that we are going to revisit in the next lecture when we talk about enforcing timing constraints on sequential circuits. This will come into play when we start adding flip-flops and doing sequential design. And with respect to FPGAs, when you run Quartus, you can generate a timing report when you synthesize your design. You guys probably haven't looked at this yet, but if you're interested, you can go back to your design from Lab 1, and you could click on TimeQuest Timing Analyzer in Quartus, and it'll show you this information for the circuit that you're putting on the FPGA. It'll show you the contamination delay and the propagation delays on the synthesized circuit. So you might say, well, who cares? Well, if we wanted to run your circuit faster, like right now you guys are all locked into 50 megahertz, right? That's what we set the timing constraint for you. But once you design your CPU and you'd like it to run a little faster, you might want to increase the clock speed, right? You might want to make the clock run faster. In fact, you might be thinking about why my CPU in my laptop doesn't run faster than 4 gigahertz or whatever it's rated at. It's because of the timing of the logic circuits. And so it all comes back to that. Unfortunately, we're not going to have time this semester to try to tweak the timing of your design. We're going to lock all your designs into 50 megahertz, which will be very easy. We won't have to worry about, because that's such a long clock period with this technology that we won't have to worry about propagation delays being too long, right? So we're giving you a very easy timing constraint. But in the real world, you'd have to optimize that if you want to speed up your design. Okay, or I should say in industry. Okay, any questions? Okay, good. That's all I have for today. We'll see you in lab, and see you back here on Monday.